Imagine taking the most delicate, microscopically precise polymer structure, like something you've engineered to build micro-robots, or maybe, I don't know, a tiny biological scaffold for single cells.
Right, the really fragile stuff.
Exactly. Now imagine taking that incredibly fragile nanoscale plastic and just throwing it directly into the path of one of the most violent, high-energy radiation beams on Earth.
Yeah, you would absolutely expect it to instantly vaporize. I mean, just poof, gone.
Right. But instead, that tiny polymer print survives, and it actually unlocks the universe's smallest secrets.
It completely upends decades of conventional physics. The idea of placing an amorphous 3D printed plastic into a massive synchrotron beamline and having it not only survive, but actually control the beam. It's a total paradigm shift.
Well, welcome to the 2PP podcast for a very special deep dive. Because you, listening to this, are an expert in two-photon polymerization, we are dedicating this entire conversation to what I can only really describe as the ultimate application dream of your daily work.
Yeah, we're looking at a fascinating head-to-head manufacturing battle here. It was published in March 2026 by researchers at the Shanghai Synchrotron Radiation Facility.
And the mission of this deep dive is to see if additive manufacturing could, well, finally step up and produce low-cost, customizable, rapidly deployable, hard X-ray focusing optics.
Exactly. So the researchers basically pitted an older additive method, projection micro-stereolithography, or PSL, directly against your domain 2PP.
A real showdown.
Yeah, they wanted to see which technology could reliably manufacture polymer compounded refractive lenses, which are known as CRLs. And they didn't just look at them under a microscope either.
Wait, no, they didn't. They evaluated them using at-wavelength metrology right there on the active X-ray beamline.
Which is the ultimate test, really.
But before we break down the printing parameters and the resins, we really have to establish why physicists at multi-million-dollar synchrotrons are suddenly so desperate for polymer 3D printing in the first place.
Right. I mean, the status quo for focusing hard X-rays relies on technology that is, well, it's almost agonizingly rigid.
Yeah, to focus these beams, facilities usually rely on Kirkpatrick-Baez or KB mirrors. But because X-rays have such incredibly short wavelengths, they don't really bounce off surfaces like visible light does.
No, they just want to blast straight through everything.
Right, so to force an X-ray to reflect and focus, it has to hit the mirror at an extreme grazing angle. And that mirror requires a height profile with a 1 nanometer peak-to-valley surface error.
Which is just wild.
Mm-hmm.
The fabrication required to achieve a 1 nanometer tolerance is staggering. I mean, it relies on atomic level polishing and incredibly restrictive metrology.
It sounds like a nightmare.
Oh, it is. The alternative to those massive mirrors is using refractive lenses made from materials with a high delta to beta ratio.
And in X-ray physics, that simply means a material that offers high refraction. So bending the light with low absorption, meaning it doesn't, eat the energy.
Right, exactly. Which historically leads you with beryllium or silicon.
But both of those materials are absolute nightmares in their own right, too. I mean, if you scale that 1 nanometer mirror error up to the size of a continent, it's like saying the tallest mountain peak and the deepest ocean trench can only be like a few millimeters apart.
Yeah, that's a great way to put it. It is literally polishing a continent until it is perfectly flat.
And if you abandon the mirrors for beryllium lenses, you're dealing with a highly toxic metal. Machining beryllium is dangerous, and it requires extreme material purity.
Because a single microscopic flaw inside that metal causes massive X-ray scattering, which just ruins the beam.
Right. So what about silicon?
Well, silicon is safer to handle, and advanced lithography can etch silicon lenses down to a brilliant 50 nanometer focal spot. But silicon has a fatal flaw for hard X-rays. It absorbs far too much of the beam's energy.
Oh, so it destroys your beam flux.
Exactly. You get a tightly focused spot, sure, but there's barely any light left in it. Plus, those etched silicon lenses are almost always limited to restrictive one-dimensional profiles just because of how lithography etching works.
So physicists are basically trapped. You can use a toxic material that scatters your light, a safe material that eats your light, or a mirror that takes atomic-level wizardry to manufacture.
Which is exactly why the researchers in this paper turned to additive manufacturing.
Right, because 3D printing theoretically allows them to create customized, two-dimensional parabolic shapes out of amorphous polymers. It's the difference between trying to, carve a complex water slide out of a solid block of granite versus just pouring a custom plastic mold.
Exactly.
But wait, if I'm a synchrotron physicist, I have an immediate red flag here. Hard X-rays carry immense thermal energy. Putting a plastic lens into a 15-kilo electron volt beam seems like a recipe for just a melted puddle of slag.
Yeah, I mean, that's the first thing anyone would think.
Mm-hmm.
But the material science has advanced specifically to answer that exact concern. The researchers didn't just grab standard prototyping resin off a shelf.
Okay, so what did they use?
They selected heavily engineered photopolymer resins designed specifically for high hardness, high elastic modulus, and exceptional thermal stability.
Ah, I see.
Yeah, the cross-linking density in these modern amorphous polymers is so robust that they can survive continuous high-energy radiation. They offer this perfect balance of cost, unbelievable precision, and total plasticity in design without degrading under the beam.
Wow. But having the theoretical resin is one thing, right? Shaping it at the nanoscale without introducing structural flaws is the real hurdle.
Oh, absolutely.
So when the researchers actually fired up the printers, they forced the older DLP-based method, PSL, into a head-to-head battle with 2PP. Let's examine the PSL approach first. They utilized three different materials: tough, HTL, and ST1400 resins. And they were aiming for a 2D parabolic configuration with a 160 micron radius of curvature.
Right, so PSL operates using a digital micromirror device as a dynamic mask. It basically projects ultraviolet light to flash cure the resin layer by entire layer.
And that sounds efficient, but there's a catch, isn't there?
A huge one. The problem is the internal chemistry of that process. When you cure an entire layer of polymer simultaneously, the polymer chains link up all at once. And as they link, they physically pull on each other.
Oh, so that creates massive internal stress locked inside the material itself.
Exactly. It's unavoidable with that method.
And we saw the devastating physical effects of that locked-in stress immediately. Because of viscosity issues with the ST1400 resin in particular, they had to alter the CAD model from a delicate, thin shell to a uniform with rectangular shell, just to try and brace the structure.
Yeah, they were basically trying to reinforce it against its own internal forces.
But even with that thicker bracing, the scanning electron microscope revealed massive macroscopic deformation. I mean, at a 100 micron scale, the PSL lenses literally warped and pulled themselves out of shape as those internal stresses failed to release.
It's a mess. And furthermore, the SEM images highlighted highly visible layer lines. The nature of flash-curing vertical layers creates these jagged, step-like artifacts all over what is mathematically supposed to be a perfectly smooth parabolic curve.
And for X-ray optics, a rough surface profile is pretty much a death knell, right?
Oh, absolutely fatal. Which brings us to the 2PP print run. The researchers used a nanoscribe photonic professional GT2 system, the PPGT2 operating in dip-in mode with a 25x objective.
And since you, the listener, work with 2PP, you know that the material properties here dictate the entire engineering approach.
Oh, 100%.
The PSO resins have a viscosity sitting anywhere from like 85 to 280 centipoise. But for the 2PP run, they used IPS resin, which has a massive viscosity of 13,600 centipoise.
Yeah, that is a wild difference. Working with a resin that thick fundamentally changes the rules of gravity and structural support during the print.
Because 2PP cures the polymer voxel by voxel, moving point by point in three-dimensional space, right?
It's not flashing a whole layer at once.
So if I'm visualizing this, printing an overhanging parabolic curve in 13,600 centipoise IPS resin is like trying to build a delicate archway out of wet clay.
That is exactly what it's like.
Because the 2PP point-by-point process is relatively slow. I mean, this print took 8 hours. That heavy, viscous top arch is going to naturally sag and collapse under its own weight long before the polymer fully cures and solidifies.
Yeah.
They must have had to entirely rewrite the CAD model just to keep the geometry standing.
They absolutely did. They introduced an arc-shaped base specifically engineered to mitigate the microscopic internal stresses, avoiding that macroscopic warping that ruined the PSL lenses.
Smart.
Yeah, and to solve that wet clay sagging problem, they adopted a trapezoidal exterior design. This geometry acts as permanent, built-in scaffolding. It provides crucial physical support for the upper curved surfaces while the laser writes them point by point.
And they also tighten the radius of curvature down to 130 microns, keeping the geometry manageable within the 400 micron effective field of view of that 25x objective lens.
Right.
And looking under the sum, the physical differences are just night and day. At a 30 micron scale, the layer lines on the 2PP prints are virtually imperceptible compared to the PSL lenses. There is no macroscopic deformation at all.
It is particularly impressive that they achieved this structural fidelity using the older generation PPGT2, honestly.
Oh, right, because the technology's already moved on from that.
Yeah, the additive manufacturing field is moving so rapidly that newer systems, like the Quantum-X, are actively optimized to print even smoother curved surfaces by utilizing grayscale lithography. I'm sure many of you listening are already using a Quantum-X for that exact reason.
Definitely.
But the fact that the researchers managed this level of flawless sub-micron topography with the older PPGT2 really proves just how mechanically robust the underlying two-photon process is.
Okay, so 2PP definitively wins the beauty contest under the microscope, but a visually smooth lens doesn't guarantee it can wrangle X-rays.
No, definitely not.
So they took both sets of printed lenses to the BL13HB beamline at the Shanghai Synchrotron Radiation Facility for at-wavelength metrology.
And to measure the microscopic flaws in the lenses, they used an incredible technique called the X-ray speckle tracking method.
How does that work exactly?
Speckle tracking is just a brilliant diagnostic tool. They insert a binary random coded mask, which is essentially a microscopic irregular grid, into the X-ray beam right in front of the lens. This grid casts a highly complex buccal pattern, which is essentially a shadow map.
Oh, I see. So think of it like shining a very bright flashlight through a warped antique window pane and casting the shadow of a screen door onto the wall.
Yes, perfect analogy. By scanning that microscopic mask in the X and Y directions, they track exactly how the shadows the speckles distort and bend as they pass through the polymer lens.
Okay, and then what?
They then feed that distortion data into an algorithm called wavelet transform-based speckle vector tracking. The math reconstructs the 2D phase, or the effective optical thickness, of the lens with mind-blowing accuracy.
Wow. So this algorithm maps the residual phase errors, which are the microscopic deviations from a perfect mathematical parabola.
Exactly. And the numerical data perfectly quantified the visual flaws we saw earlier under the electron microscope.
Right, let's look at the numbers. The PSL lenses, using the HTL and tough materials, had a root mean square phase error of around 0.02 lambda. In X-ray optics, an error of lambda over 14 is generally the minimum standard for usability, so 0.02 technically clears the bar.
It clears the bar, yeah, but barely.
Right, because when they ran a Zernike polynomial analysis on the PSL lenses, the underlying optical behavior was a complete mess.
Yeah, it was. So Zernike polynomials act essentially as a highly specific diagnostic chart for lenses. It's very similar to an eye doctor, identifying exactly what kind of astigmatism or blur a patient has.
So it breaks down the raw optical errors into specific categories of geometric aberration.
Exactly. And the PSL lenses suffered from massive primary coma and severe mid-order aberrations.
And a primary coma aberration means the X-ray beam hits the lens and smears out, right? Like looking like a comet with a trailing tail rather than focusing into a sharp microscopic dot.
Yep, that's exactly what it looks like. And the cause of this is entirely those layer lines we talked about.
It makes sense. Imagine throwing a handful of bouncy balls down a jagged concrete staircase versus rolling them down a perfectly smooth ramp.
Right.
On the smooth ramp, the balls stay grouped together. That's a tightly focused beam. On the staircase, every time a ball clips the edge of a stair, it violently scatters in a random direction. The PSL layer lines acted like a staircase, scattering the X-rays into that comet tail smear.
While the 2PP print, however, was the smooth ramp.
Let me guess, the speckle tracking data backed that up.
Oh, it heavily supports that conclusion. The 2PP lens printed with IPS achieved a staggering 0.08 lambda RMS residual phase error.
Wow.
Yeah, that is an order of magnitude better than the worst PSL material. The Zernike analysis proved that the continuous voxel-by-voxel 2PP process virtually eliminated the primary coma.
But wait, looking closely at the specific Zernike data chart in the paper, I have to challenge the idea that the 2PP lens was completely flawless.
Oh, okay, let's hear it.
The Z11 term on the chart, which represents primary spherical aberration, was actually relatively large. Furthermore, there were notable fluctuations in the orthogonal terms representing astigmatism.
That's true.
So if 2pp is supposedly the absolute pinnacle of nanoscale precision, why didn't the mathematical CAD model translate perfectly into the polymer? Why are we seeing spherical aberration and astigmatism in a lens that took 8 painstaking hours to print?
Well, that observation cuts to the very heart of working with polymers at the nanoscale. The aberrations aren't a failure of the two-photon optical resolution, right? They are artifacts of physical chemistry and mechanical hardware.
How so?
First, consider polymer shrinkage. Even when using highly optimized low-shrinkage resins like IPS, the chemical cross-linking process still results in a tiny fraction of volumetric change during development.
Oh, right, because it cures and shrinks slightly.
Exactly. And when you are evaluating performance, against a fraction of an X-ray wavelength, even a submicron volumetric shift causes the parabola to physically pull itself slightly out of shape as it solidifies. That shrinkage manifests directly as spherical aberration.
So the CAD math is perfect, but the physical chemistry of the developing solvent slightly betrays you.
You could say that, yeah. And secondly, the astigmatism is deeply tied to the mechanical calibration of the PBGT2 equipment itself.
Really? The hardware itself causes it.
Yeah, when a 2PP system prints a structure larger than its immediate field of view, it has to physically move the horizontal translation stage to stitch the writing fields together.
Ah, I see where this is going.
Right. Any microscopic mechanical bias or deviation in that stage's movement, say, tracking slightly differently in the X direction versus the Y direction, translates directly into a structural aberration in the polymer.
It's an accumulation of mechanical and chemical realities. But as any 2PP expert listening knows, resin shrinkage and translation stage calibration are hurdles that can be aggressively dialed in and fine-tuned in future iterations.
Exactly. It's a known variable.
And the core fact remains. Despite those minor aberrations, the single 2PP lens so completely obliterated the DLP method in optical performance that the researchers immediately escalated to the final application dream.
They needed to see if 2PP could produce a massive functional array. Because single lenses are useful for testing, but synchrotrons require compound arrays to actually achieve their focal goals.
So what did they build?
The researchers used 2PP to print a 65-element train-type parabolic CRL array. They perfectly aligned 65 individual biparabolic lenses in a continuous row.
Wow, 65 of them.
Yeah. Each lens featured a 100-micron radius of curvature, and they were spaced exactly 10 microns apart at the base.
And to test this 65 lens train, they placed it directly into the path of a 15-kilo electron-volt hard X-ray beam, and they left it there for hours of continuous irradiation.
And you know what happened?
Did it melt?
Nope. The structural integrity of the IPS polymer held up flawlessly. There was not a single observable trace of thermal damage or degradation. The amorphous polymer completely survived an environment that intuitively should have destroyed it.
The thermal stability is staggering. But, the optical performance is what really matters to the beamline physicists. A 15 keV beam is a massive, chaotic wave of high-energy light.
And by forcing that wave through this 65-element polymer array, they achieved incredibly tight focal spot sizes, 6.4 microns horizontally and 6.8 microns vertically.
That's tiny. And for anyone who isn't a synchrotron expert, the headline number here is that they achieved a massive flux gain of 220.
Yeah, a flux gain of 220 means they successfully wrangled that chaotic X-ray energy and squeezed 220 times more photons into that tiny 6-micron focal spot than would have naturally hit it.
That is exactly what high-energy physicists are desperately searching for, right?
Yeah.
Massive flux density, microscopic spot size, and zero X-ray absorption from the lens material itself.
Exactly. It is like creating a microscopic compound insect eye that focuses blinding radiation to a perfect pinprick.
But looking at the focal length measurements for that 6-micron spot, there is a very bizarre quirk in the data.
Oh, the focal point separation.
Yeah. The horizontal focal length, the distance from the lens to the focal point, was measured at 643 millimeters. But the vertical focal length hit at 598 millimeters.
That's a big difference.
Right. The beam is focusing almost 45 millimeters apart, depending on the axis, like having your left eye focus at a completely different distance than your right eye. What physically causes that focal point separation?
Well, this requires us to look back at the Zernike analysis we discussed earlier. Remember the primary astigmatism and spherical aberrations caused by polymer shrinkage in the translation stage?
Right, the Z11 stuff.
Yeah. In a single lens, those structural errors were incredibly minor. But an array fundamentally changes the math. When you stack 65 of these lenses in a continuous train, the sheer physical length of the optical path amplifies those tiny single-lens errors.
Ah, I get it now. A microscopic stage calibration error that causes a single lens to bend the light slightly wrong is compounded.
Yep.
The X-rays pass through the first lens, pick up a tiny astigmatism, hit the second lens, amplify the astigmatism, and multiply that error 65 times.
Exactly. And by the time the beam exits the final lens, the vertical and horizontal focal points have drifted 45 millimeters apart.
This specific amplification of error points exactly to the next major frontier for 2PP in X-ray optics, doesn't it?
It really does. The researchers concluded that the printing fidelity itself is absolutely ready. The 2PP hardware and the IPS resins are fully capable of creating the necessary structures.
So the solution to the astigmatism isn't necessarily a better printer.
Not at all. It's smarter digital modeling.
Oh, so you don't just feed a perfect mathematical parabola into the nanoscribe anymore. You have to design a CAD model that is intentionally distorted.
Precisely. You calculate the exact polymer shrinkage rate and the known mechanical aberrations of the translation stage, and you bake that mathematical compensation directly into the 3D model before you ever hit print.
Wow. So it creates a sophisticated closed-loop system of design, print, measure with speckle tracking, and pre-compensate the next model.
Yeah, you purposefully print a mathematically flawed lens so that when it physically shrinks, it shrinks into absolute perfection.
So what does this massive, successful beamline test actually mean for you, the 2PP expert listening to this? It means your daily work isn't confined to the realm of micro-robotics or cellular scaffolds anymore.
No, it's so much bigger than that now.
This paper from the Shanghai Synchrotron Radiation Facility establishes definitively that two-photon polymerization is a highly viable, immediately practical pathway for manufacturing the next generation of custom synchrotron X-ray optics.
And that 2PP vastly outperformed DLP-based methods in minimizing residual phase error, in suppressing coma scattering, and in maintaining absolute structural fidelity.
It emphatically proves that engineered polymer 3D printing can survive the intense radiation of a beamline, deliver the massive flux density that silicon lenses completely fail to provide, and bypass the toxic manufacturing hazards of beryllium mirrors.
It's an incredible achievement.
And I want to leave you with a final provocative thought to mull over. We just spent this entire deep dive analyzing a 65-element array of simple parabolic lenses, just basic geometric curves.
Very basic.
But you know the ultimate geometrical freedom that 2PP allows. You aren't restricted to parabolas. If a simple curved shape printed in IPS can survive 15 keV hard X-rays and achieve a flux gain of 220, what happens when 2PP experts start designing complex, apochromatic 3D metamaterial lenses?
Oh man, we're talking about internal geometries and sub-wavelength architectural structures that conventional glass and mirror manufacturers couldn't even dream of carving.
Exactly. Lenses that could theoretically correct for multiple wavelengths of X-rays simultaneously through physical metamaterial manipulation.
The possibilities are endless.
The barrier to controlling the most high-energy light in the universe is no longer the manufacturing tool. The limit is no longer the agonizing 1 nanometer tolerance of polishing a Kirkpatrick Bayes mirror. The limit is purely the imagination of the designer sitting at the CAD software.
It really is.
Thank you for joining us on this special deep dive.
We look forward to seeing what you design and print next.
The universe's smallest secrets are waiting to be focused. We'll see you next time.